I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine a world where traveling between cities is faster than flying, quieter than trains, and cleaner than electric cars, where a journey that normally takes 6 hours shrinks to 40 minutes. That's the promise of the Hyperloop, a system once dismissed as sci-fi, but now advancing so quickly that governments, engineers, and defense planners can't afford to ignore it. At its core, the idea is deceptively simple. Take a sealed tube, remove most of the air, float a pod using magnetic levitation, and accelerate it to near-supersonic speeds with linear electric motors. Low drag, low energy consumption, and the speed somewhere between an airliner and a rocket. But what makes Hyperloop fascinating is not just the physics, it's the radical engineering behind it. Instead of wheels and rails, you have contactless Maglev, using either high-temperature superconductors or electromagnetic suspension. Instead of jet fuel engines, you use linear induction motor stators embedded along the track. Instead of full vacuum, you maintain a controlled low-pressure environment around 100 pascals, which cuts aerodynamic drag to less than 1% of what you'd see at sea level. And because there's almost no friction, the energy cost per passenger kilometer is dramatically lower than planes, EVs, or high-speed rail. All of this means two things. Hyperloop isn't just fast, it's efficient. And it's not just efficient, it's scalable. But building something this ambitious comes with equally ambitious challenges. The tube must handle microleaks, thermal expansion, and dynamic pressure loads from pods traveling at Mach 0.8. Maglev systems must maintain millimeter-level stability at extreme speeds. Vacuum pumps must operate along hundreds of kilometers without failing. Emergency braking systems must safely decelerate from 800 to 1,000 kilometers an hour inside a sealed tube. And on top of that, you need earthquake-resistant pylons, AI-driven traffic control, and near-perfect synchronization between propulsion, levitation, and environmental systems. This is why the Hyperloop has become a magnet for innovation. Engineers are testing carbon fiber pressure shells, plasma-based leak detection, high-power grid interfaces, and predictive maintenance algorithms using digital twins. Every component, from the pod's battery pack to the vibration dampers, is being re-engineered for reliability at speeds humans have never traveled inside a tube before. But technology is only half the story. Then there's safety. And, of course, regulation. What laws apply to a tube going 1,000 kilometers an hour between cities? Railway laws? Aviation laws? Something entirely new. And no wonder defense agencies are watching. A high-speed tube corridor is both an economic asset and a strategic vulnerability. Acceleration profiles, dual-use logistics capabilities, and critical power infrastructure bring national security implications no one can ignore. Then comes the shocker: cost. People assume Hyperloop is too expensive until they see real numbers. Because the tube is elevated and modular, land acquisition drops dramatically. Because pods are lightweight and Maglev is contactless, maintenance is lower than rail. And because energy demand is low, solar-covered tube segments can offset a meaningful portion of operating costs. It's not cheap, but it's far more realistic than the early critics claimed. And that brings us to the moment where everything changed. And then came the milestone that shook the entire industry. In 2024, China achieved stable Maglev levitation at 1,000 kilometers an hour on a full-scale test track in Shanxi. Not theory, not simulation, real hardware, real results. China's strategy is straightforward. Build long test corridors, industrialize Maglev components, and accelerate toward the world's first operational national Hyperloop network. Meanwhile, in the United States, growth is taking a different but equally powerful form. The U.S. Hyperloop market is booming, expanding at 45% per year and projected to reach $7.5 billion by 2030. American companies are aggressively developing modular tube manufacturing, high-efficiency propulsion stators, and standardized safety systems that could define global certification. The U.S. focus is clear: commercialization, freight networks, and continent-scale deployment. India is pursuing ultra-long Hyperloop corridors aimed at connecting major cities with unprecedented travel times. These ability studies for routes exceeding 500 kilometers are already underway, backed by strong government interest in cutting emissions and relieving extreme congestion. India's approach blends mass mobility demand with next-generation infrastructure, making it one of the largest potential Hyperloop markets on Earth. Europe is taking the regulatory lead. The EU is building certification tracks, engineering test beds, vacuum tube safety guidelines, and cross-border interoperability standards. Their goal: make Hyperloop as internationally compatible as aviation. And the Middle East? It has the ambition and the geography to build continent-spanning networks faster than anyone else. With long, straight corridors, smart city megaprojects, and heavy investment in future mobility, the region could become the first to deploy commercial Hyperloop at scale. All this adds up to a single reality. What started as a wild idea is now a global race, one where speed, engineering talent, manufacturing capacity, and regulatory breakthroughs decide who leads the next century of mobility. Thanks for watching. Subscribe, follow, or visit IDSTH.com for more cutting-edge defense and tech insights. See you in the next one.